Hello, everyone. Thank you for the introduction. My name is Joseph Karam. I'm a master's student in the Sensors and Integrated Microelectronics Lab at Oregon State University, and I'm really honored to be here to give the talk today on a shape-sensing stretchable sensor grid towards cameraless motion capture. Without further ado, I'll get started. I'd like to just give a brief outline of the presentation. I'll start with the motivation for this project. Then I'll move into a discussion on the self-sensing stretchable strain sensors designed for the system. Then I'll give an overview of the design and fabrication of our stretchable sensor grid. I'll discuss the testing and results of the system, and then I'll give a summary of the overall project, the findings, and any future work. So we were seeking an array of sensors capable of measuring strain as well as performing position estimation. These sensors need to withstand high strain, and the housing for the sensors also needs to be stretchable. A system like this could have applications in the fields of wearable electronics as well as cameraless motion capture. Whereas most motion capture systems today consist of cameras that track IR markers on an object, a system like this would not require any cameras, allowing it to be more versatile, used in different environments where cameras are not always readily available. Now to discuss the strain sensors. So our strain sensors are stenciled serpentine wires. They're made of a liquid metal paste. This material is a mixture of gallium, indium, and tin, and we sonicate it with nickel nanoparticles, giving it a toothpaste-like consistency. When we encase the material in silicone, we can create liquid metal wires that can be subjected to high strain and still carry both power and electrical signals. As shown in the figure on the left, a single liquid metal strain sensor is approximately 50 millimeters in length at idle. However, it's shown on the right under strain being stretched up to 100 millimeters. And in fact, testing has shown that these wires can be stretched up to even higher strain and still retain continuity. So under strain, a liquid metal wire's length will increase and its cross-sectional area will decrease while it's encased in the silicone. Therefore, since resistance equals resistivity times length over cross-sectional area, a liquid metal wire stretched to double its original length should theoretically see a 4 times increase in its resistance. This relationship can be represented by the following equation: R over R naught equals L over L naught squared, where R naught and L naught are the wire's resistance and length at idle, and R and L are its resistance and length under strain. This equation can be rearranged algebraically to solve for the length of a liquid metal wire under strain, provided the other quantities are known. R naught can be measured when the strain sensor is being fabricated. L naught can be measured simply with a ruler. So as long as we can figure out R, we'll be able to calculate our length of the strain sensor. However, how do we find this resistance? Well, we model our strain sensor as a variable resistor called R, and we put it in series with a chip resistor of a known value, say 2.1 kiloohms. When that chip resistor is pulled up to 3.3 volts or any known voltage and the strain sensor is pulled down to ground, this forms a voltage divider. Normally, with a voltage divider, provided your resistances are known, you can solve for the voltage between them using the standard voltage division equation. However, here, if we measure the voltage between the two resistors with an analog to digital converter, we can rearrange the voltage division equation to solve for the resistance of the strain sensor rather than the voltage between the two resistors with the following equation: R equals V times 2100, or whatever that known resistance is, over 3.3 minus V. So with this equation, we now have a way to know the resistance of our strain sensor under strain. To interface with our strain sensors and perform measurement and communication, a centimeter scale printed circuit board was designed. From here on out, I'll refer to it as a node. Each node contains a microcontroller with built-in ADC, and that's what we use to measure that voltage between the strain sensor and chip resistor. And we also use the microcontroller to send all the data collected to an external controller through I2C communication. Each node also contains an inertial measurement unit. This IMU has a 3-axis gyroscope and 3-axis accelerometer with built-in filtering algorithms. So these IMUs are used to help perform position estimation for our nodes. On board each node is also the 2.1 kilo ohm chip resistor previously referenced that forms the voltage ladder with our strain sensor. And lastly, we have copper pads on the bottom side of each node, and these are used to connect our liquid metal wires directly to our PCB. So we designed and fabricated a single strain sensor node pair to test the idea before we built a full grid. We used EcoFlex silicone to encapsulate the liquid metal wires in our rigid PCBs. And as shown in the figure on the top, we used a stiffer dragon skin silicone just on the top layer around each of our rigid PCBs. This helped to prevent any tearing between the soft silicone and the more rigid PCBs at those junctions. Our liquid metal wires are made using 100 micron thick metal stencils, and we create liquid metal vias to interconnect our layers. These vias are formed by placing metal dowels down in our silicone as it's being poured. When these dowels are removed, we have holes that connect our layers, and these are filled with liquid metal. So these are electrical vias that connect our liquid metal wires to the backside of our nodes. On the top shows a fully fabricated single node, single strain sensor. You can see the strain sensor, the node, a 4-wire liquid metal bus that we use to power the node, as well as carry our clock and data lines for I2C, and then a connector board to connect the node to the outside world. And the figure on the left is a layer-by-layer stack-up of our overall sensor. We have alternating layers of silicone and liquid metal with our connector board and node rigid PCBs. And the blue cylinders indicate the liquid metal vias interconnecting our layers. The strain sensor was subjected to repeated strain to test its performance. The figure on the left shows our measured strain sensor response compared to a y=x² quadratic fit line. As you can see, it matched closely the expected behavior, albeit with some deviation at higher levels of strain. And this follows in our figure on the right, which shows the calculated strain sensor length compared to ground truth. Our ground truth data was collected using a state-of-the-art motion capture system with cameras and IR markers for tracking. We saw a maximum error between the two lines of 2.5%, and this was most visible at the higher levels of strain. Inaccuracy in our strain sensor can be caused by a number of factors. For example, we noticed variations in our stenciled liquid metal wire thickness and our line width, as well as impeded strain around the node that's caused by the thicker silicone used in that area. These are inconsistencies in manufacturing that could be solved down the road. However, for the time being, a calibration scheme was devised to counteract this error. We subject a newly fabricated strain sensor to high strain while collecting ground truth data. And then rather than using the original L=L0 times R/R0 to the 1/2 equation to calculate the strain sensor length, we adjusted the exponent to 1/x rather than 1/2, and we adjust this x value to more closely align our sensor data with the ground truth data. This yields a unique x value for each of our strain sensors that counteracts the intrinsic error seen in them. Once our strain sensor was calibrated, we found that x was 1.949 for that specific sensor, and when we reran the test from the previous slide, we saw an even better result with a maximum error of 2%. Moving on to the full stretchable sensor grid. Our grid is comprised of 24 strain sensors connected to 16 nodes in 2 axes. We have one single I2C bus that connects all of the nodes to an external microcontroller, which we use for data collection. So we have 17 total devices on this I2C bus. The bus also includes a 5-volt power rail. Each node contains a 3.3-volt low dropout regulator on board for local power regulation. And our ADCs and IMUs are all pulled at a frequency of 50 hertz. In reality, the hardware can run faster. However, due to the bus capacitance on our I2C line caused by the thick liquid metal wires, as well as the number of devices on our bus. We're limited to a frequency of 50 hertz, which is good for most applications in this field. On the bottom is the layer-by-layer stack-up of our full grid. It's very similar to the single node prototype, albeit with an extra liquid metal and extra silicone layer, since we now have strain sensors on multiple axes, so we relegate those to separate layers. The typical strain sensor resistance at idle is about 20 ohms, and the typical single wire resistance is about 5 ohms in our I2C bus. And shown here is the fully fabricated stretchable sensor grid under 35% uniaxial strain. As you can see, when it's stretched in one axis, the nodes tend to move closer to each other in the other axis. A calibration set was created for all 24 strain sensors following the same process used for our single prototype, and the grid was subjected to uniaxial strain. Each segment length was calculated from the measured data, and then the position of each node in the grid was estimated by adding all of the segment lengths together, with the node at 0, 0 as a reference. As shown in the figure here, the black circles indicate the node positions at 0% strain. The red circles are our ground truth node positions, and the blue X's indicate our calculated node positions. We achieved an average segment error of 0.63%, with our worst segment showing an error of 1.8%. The IMUs on board each node were also tested for their accuracy. Node orientations were reconstructed from the IMU data, and a mesh of the sensor grid was generated from the estimates. As shown in the figure on the right, the generated sensor grid is seen to closely match the general orientation of our actual grid, indicating that our IMUs were giving us accurate data. A variety of such tests were run with various objects, such as cylinders and spheres, and they all yielded similarly positive results. To summarize, a stretchable sensor grid with 24 strain sensors and 16 IMUs was designed and successfully fabricated. Our strain sensors show a maximum error of 2% and more than 50% strain. The node positions in our grid are estimated with an average error of 0.6% using the strain sensor data, while our grid is at 20% uniaxial strain. And the node orientations in our grid are successfully estimated using the IMU data. So future work will seek to leverage the strain sensor data and IMU data simultaneously to allow for the full reconstruction of soft bodies as well as the cameraless motion capture.